Okay, I'm also going to do a walk down memory lane, but only 4 years back. That's only 2 Moore's Law generations. But I'm doing it because the past is prologue. There was a lot of innovation in the ARM v7 days that I think we can learn from in the ARM v8 days. We got HPC out of the boxes we were building. We were only really building for a very specific target and doing things like taking everything out that wasn't HPC, monolithic kernels, using tools, the Sandia Strongbox. They had tools that would, evaluate your compute to communication overhead and qualify your data chunks for you. You'll notice that poster there. That was at the last time IEEE supercomputing was in Denver. The Boston Limited booth had a Cal SATA powered cluster. HP Moonshot had a Cal SATA powered cluster. I think the ARM booth had a Cal SATA box. Cal SATA was very innovative in looking at ARM v7 energy efficiency improvements, and also further extended what you could put on die, on package, on board to integrate some of the other things that would keep you along Moore's path, NOx on board, mesh, IPC. So it was ARM v7 at Cal SATA was very helpful for the ARM v7 HPC community in general, and they made some great products. That was a good show for them. ARM had a box. I think that was the year they had a box. I think there was a Cal SATA booth at that conference too. Let's see. Oh, this one. Shortly after that conference, we had one of the boxes we built at MIT was the solar-powered supercomputer. What you can take from that was we had a single conductor for both data and power. It worked good enough. We probably hit a scalability limit right there. The great thing about the OMAP 4 as opposed to the earlier OMAP 3, the TI OMAP 3 that was on the Strongbox was it was multi-core. We had SMP kernels. We could ignore things like blocking and barrier synchronization. That helped our codes out a lot. And guys like Clint Whaley at UTSA and some folks at Vesprix and other folks from Oak Ridge and started moving netlib libraries over to ARM v7. We had a great atlas that would optimize BLAS kernels for us. We started getting some noticeable improvements on ARM v7 synthetic benchmarks. We still weren't running HPC codes on ARM clusters then, but we were running significant benchmarks and getting great energy efficient numbers. Not great raw numbers. We weren't on the top 500, but we were looking towards the green 500. And so that brings us to where we're at today. We moved through Odroid, so we've moved up yet to another class of ARM v7 on the Samsung silicon. That was great. You can do quite a bit with we were running the various revs of Linaro that came out for ARM Cortex-A15 because Linaro was revving quicker back then. Most of the devs in my lab are Debian folks, and we've been moving all of the HPC packages we can think of over to our HPC library, which is very Debian-centric, but it's also very ARM-centric now. It's called opennovation.org. I wouldn't go to it yet. November 1 might be a good time to go to it, but I can talk to you afterwards and get you into the beta site if you want. All the HPC codes we run at the student cluster competition are there. There's probably 200 of them. We're moving more over as we discover them. And we're progressing now to embedded ARM v8 and looking at what you can do with ARM v8, various kinds of ARM architecture cores, and if there's any embedded accelerators in there using shared memory tricks. There's a lot of innovation going on right there. We, in this student cluster competition, we have had ARM sponsorship through Cavium, but now we're going to look at the next generation of integrating ARM with, we didn't quite have the ARM performance libraries back then. We were still using our own generated BLAS kernels. But between ARM performance libraries, the new silicon, and accelerators, we really like the path of ARM v8. So don't go to opennovation.org yet. But if, like I say, you can come over and talk to either myself or Mitch. We're MIT ARM at mit.edu. That goes to both of us. And I can talk to you afterwards.